Hey everybody, and welcome to this video on multiplying and dividing radicals. So let's make it happen. Alright, please consider the three examples in front of us. And in each, we have some numbers and we're taking roots, both square roots and cube roots, and multiplying. But in some instances, we're taking the roots of each of the numbers individually and then multiplying those roots. And in some instances, we're multiplying the numbers first and then taking the roots of that product. So what I'd like you to do is to pause the video and please evaluate each of these expressions and then compare them to one another. All right. In each case, it appears that when we're taking roots and multiplying numbers together, the order in which we do the operations doesn't matter. That is, we can take each of the individual roots first, then multiply, or we can multiply the two radicands first, and then take the root, whether it's a square root, or a cube root, or whatever root. Of course, it's got to be a square root and a square root, or a third root and a third root, etc., etc. It couldn't be a square root and a cube root. It's got to be the same root. And so in general, that's going to be the case, that we have the option of either taking the individual roots first and then multiplying, or multiplying the radicands together and then taking the root. Now, I'll be honest, there are some times when this is not going to be true, namely when both of the radicands are negative numbers. But we're not quite there yet, so for now, we're going to say that this always works. Now, how could this property be helpful for us? Well, let's check out a few more examples. Alright, so for example, the square root of 27 times the square root of 3. I have no idea what the square root of 27 is. I know what the square root of 25 is, that's 5, so the square root of 27 should be a little bit more than 5. And the square root of 3 is somewhere between 1 and 2, but I have no idea what the product of these two is right now. But I do know that we do have the option of rewriting this as the square root of 27 times 3. When we're taking roots and multiplying, we can either take the root first, like in the original example, or we can multiply first and then take the root. Now, why would this be helpful? Well, 27 times 3 happens to be 81, and 81 happens to be a perfect square, of which we know the square root, that's just going to be 9. So even though the square root of 27 and the square root of 3 are each really, really long decimals that go on forever and ever and don't repeat, their product is just 9. I think that's really cool. How about another one? The square root of 8 times the square root of 2. I don't know what the square root of 8 is. I don't know what the square root of 2 is. But I do know that we have the option of writing this as the square root of 8 times 2. And 8 times 2, that's a nice number. That's 16. And 16 happens to be a perfect square, and we know its square root, namely 4. All right, last example. The square root of 7 times the square root of 20. I don't know what the square root of 7 is. It's somewhere between 2 and 3. And I don't know what the square root of 20 is. It's somewhere between 4 and 5. And so their product could be anywhere between 8 and 15. That's not very accurate. I don't know. But I do know that we can write this as the square root of 7 times 20. And 7 times 20 we know is 140. Now in this case, it happened to be that we didn't get a perfect square as our radicand. But that's fine, because now, knowing that these are going to be equal to the square root of 140, we can do a much better job estimating. 140 is very close to 144, so the square root of 140 will be just under 12. So maybe we'll call it about 13.9. So in this case, being able to multiply those radicands together made it a lot easier to estimate. All right, we got 3 more examples there on the bottom. Why don't you pause the video and use this property to find or estimate these products. All right, here's some multiplication problems in which we have integers and radicals all over the place. For instance, 3 times the square root of 10 multiplied by 5 times the square root of 2. Now, even though I may have said it out loud, it's really helpful to think about this problem in this way. What we really have on our hands is 3 times the square root of 10 times 5 times the square root of 2. And since this is all multiplication, we're free to carry it out in whatever order we would like. So what I tend to do is to multiply the whole numbers together and multiply the radicals together. And in this case, we end up with 15 times the square root of 20, which we can write as just 15 root 20. Or, in our second example, 3 times the square root of 5 times 2 times the square root of 5. Again, this is just 3 times the square root of 5 times 2 times the square root of 5. Now, note, I'm writing this step out each time just to show exactly what's going on. But in general, when you look at this original problem, what I tend to do is just multiply the integers together. So in this case, the 3 and the 2, and multiply the square roots together, or the cube roots, or whatever they may be. In this case, the square root of 5 times the square root of 5. Now, 3 times 2 is 6. That's great. And the square root of 5 times the square root of 5, you can think of that in two ways. Well, the square root of 5 times the square root of 5 is the same thing as the square root of 5 times 5, also known as 25. But 25 is a perfect square. The square root of 25 is just 5. So we end up with 6 times 5, which is 30. The other way to think about this is, by definition, the square root of 5 times the square root of 5 equals 5. That's all the square root of 5 does. Eats the number such that when you multiply itself, you get 5. So in this example, we ended up just getting a nice integer product, which will happen some of the time. All right, why don't you pause the video and give these next two a try. All right, just a few more examples before we move into our next skill. So here we've got some multiplication that again involve integers and radicals all over the place, but we're multiplying one term with an integer and a radical by a set of parentheses with multiple terms in them, each containing integers and radicals. And the question is, how do we handle this? We're going to handle this in exactly the same way that we always have. Whenever we see multiple things inside of parentheses, we're going to use the distributive property. So for instance, in our first example, all we're going to do is we're going to multiply 2 times the square root of 5 by both 3 times the square root of 2 and by negative 6 times the square root of 5. All right, again, we're going to handle the integers with the integers and the radicals with the radicals. So for our first set of multiplication, 2 times 3 is 6. The square root of 5 times the square root of 2 is the square root of 10. For our second set of multiplication, 2 times negative 6 is negative 12. And the square root of 5 times the square root of 5 is 5. And so we end up with 6 times the square root of 10 minus 60, or negative 60 plus 6 times the square root of 10. Absolutely, either way is totally fine, but by convention, people tend to like this second way a little more. They like saying the integer component before they say the radical component. So just putting it on your radar, and that's something I'm probably going to do a lot. All right, one more example together before you try some on your own. In our second example, just like we did before, we're going to distribute this negative 4 times the square root of 8, and we're going to multiply that by 3 times the square root of 2 and by 5 times the square root of 8. So let's see what happens. Negative 4 times 3 is negative 12. The square root of 8 times the square root of 2 is the square root of 16. Going to our second set of multiplication, negative 4 times 5 is negative 20. The square root of 8 times the square root of 8 is 8. All right, the square root of 16, that happens to be a nice number. That's just 4. And so in this case, we end up with a nice integer product, namely negative 208. Sometimes our products will simplify a little bit, like in the first example. Sometimes our products will simplify a lot of it, like in the second example. Sometimes they won't even simplify at all. All right, why don't you pause the video and try these next two on your own. All right, now we want to explore what happens when we start dividing radicals by one another. And to motivate that conversation, here are 3 roots of fractions. And what I'd like you to do is to simply pause the video and please find the roots of these three fractions. Alright, I hope that wasn't too tough. Now if we look at the first example, the square root of 9/4, all we really had to do was find the square root of 9, which is 3, and the square root of 4, which is 2. In our second example, all we needed to do was find the square root of 25, which is 5, and the square root of 64, which is 8. And in our last example, all we needed to do was find the third root of 27, which is 3, and the third root of 64, which is 4. So I think we very easily could have rewritten the three of these as fractions, in which the numerator and the denominator each had the roots taken individually. And so we see that, like when taking roots and multiplying, when we're taking roots and dividing, the order doesn't matter. You can take the root of the numerator and denominator individually and then do the division, or you can do the division and when you find the quotient, take the root of that, whether it's a square root or a cube root or what have you. And in general, this is going to be the case. Now, when might this property be helpful for us? Well, let's take a look at this first example. The square root of 80 divided by the square root of 5. I have no idea what the square root of 80 is. I have no idea what the square root of 5 is. But I do know that we can rewrite this as the square root of 80 over 5. And 80 over 5, or 80 divided by 5, happens to be a very nice number. That happens to be 16. And 16 is a perfect square. It has a very nice square root, namely 4. So rewriting that initial example, instead of taking the roots first and then dividing, by dividing first and then taking the root, that allowed us to find the quotient, no problem, and we got the nice integer quotient of 4. All right, let's take a look at our second example. And here we've got integers and radicals going on. And like we did before, I would take care of the integers on their own, and I would take care of the radicals on their own. So 14 divided by 2, that's 7. And the square root of 108 over the square root of 12, we can rewrite as the square root of 108 over 12. And 108 divided by 12 happens to be a very nice number, namely 9. And 9 has a very nice square root, namely 3, and therefore our quotient is just going to be the nice integer 21. And so we get the idea. Let's do one with third roots real quick. I don't know what the cube root of 54 is. I don't know what the third root of 2 is, but I do know that we can rewrite this as the third root of the fraction 54 over 2. And it happens to be that 54 over 2 is a very nice number, namely 27, which does have a perfect third root, namely the integer 3. And last but not least, I don't know what the square root of 56 is. I don't know what the square root of 7 is, but I know that we can rewrite this as the square root of the fraction 56 over 7. 56 over 7 is 8, and note that we don't get a nice perfect square here, so we're not going to come up with an integer answer here, but at least simplifying that original problem into the square root of 8 made it a lot easier for us to estimate it. 8 is just a little bit less than 9, so its square root should be a little bit less than 3. Let's put this at about 2.7. All right, and why don't you now pause the video and take care of these last 4 problems using this property. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.